In this video, we are going to study regarding the design of two-way slabs. Already earlier to this video, already we have covered the basic theory regarding the design of two-way slab. So in this video, let us try to solve a problem on two-way slab. So let us see the question. Design a two-way slab for a room size of 4 meters by 5 meters. So Lx will be 4 meters, Ly will be 5 meters. Always Ly will be the longer span and Lx will be the shorter span with discontinuous and simply supported edges on all the sides. So we have discontinuous and simply supported edges on all the sides with corners prevented from lifting to support. So with corners are restrained so as to support a load of 4 kilonewton per meter square. Adapt M20 and Fe415 steel. So Lx is given, that is 4 meters, Ly is 5 meters. So first let us FCK is 20 Newton per mm square, Fy is 415 Newton per mm square. Right? This is not cube, this is square. So first we have to calculate, we have to see the ratio, Ly by Lx ratio, whether it is one-way slab or two-way slab. So always longer span to the shorter span, that is Ly by Lx, that is 5u divided by 4 will be equal to 1.25. So if the ratio, if it is less than 2, we can say it as a two-way slab. So as the ratio is 1.25, we can say that we have to design this slab as a two-way slab. So two-way slab supported on all the edges with the provision for torsion at the corners. So we have to design the torsional reinforcement also. Then next let us try to calculate the depth of the slab. So if you see the span is more than 3.5 meters, so let us assume L by D ratio, that is span to the depth ratio as 25. So therefore L by D ratio is equal to 25, therefore depth will be equal to span divided by 25. So therefore what happens is that 4000 divided by 25, if you see, we will have answer as 160 mm. So let us adopt an effective depth of 145 mm and overall depth of 170 mm. So we have assumed what you can say more than this, overall depth as 170 mm. Then next let us try to calculate the effective span. So effective span will be equal to clear span plus effective depth. So therefore like 4 plus effective depth, you have taken it as 145 mm. Therefore effective span will be 4.15 meters. Then next let us try to calculate the loads. First one is self weight of slab. So if you see the depth of the slab is 170 mm. So therefore 0.17 multiplied by density of concrete, that is 25 RCC, that is 4.25 kilonewton per meter square. Then next live load on the slab, already it is given 4 kilonewton per meter square. Let us assume a floor finish of 0.6 kilonewton per meter square. So if we are going to add up all these three loads, 4 plus 4 plus 0.6, total working load will be equal to 8.85 kilonewton per meter square. Then next is design ultimate load. So we have to multiply it by 1.5. This ultimate load will be equal to 1.5 multiplied by 8.85. So therefore it will be 13.275 kilonewton per meter square. Then next let us try to calculate the ultimate moment and shear. So we have to refer the IS code so as to calculate this moment and shear. So first we have to see what is the Ly by Lx ratio. As we have already calculated, it is 1.25. So therefore let us try to calculate from the table which is given in the IS code. So if you see here, we have the IS code as 456. In annexure C, they have given slab spanning in two direction. So they have given it for simply supported slab. Ours is a simply supported slab, and for that bending moment coefficient they have given in two directions at right angles, simply supported on all the four sides. So this table is applicable to us. So therefore now Ly by Lx ratio is 1.25. So here Ly by Lx ratio we have, that is 1.2 we have, 1.3 we have. So in between these two values we are going to get the values, that is alpha x and alpha y. So if you see alpha x will, if you interpolate, you will get answer as 0.076. So if you see 1.2 and 1.3 we have. So therefore this will be so as if you see this, they have given it as with the corners prevented from lifting to support. So we have four discontinuous edges, and here like with the provision for torsion at the corners we are going to refer this, and for other slabs we can refer this. So if you see this 1.2 and 1.3, somewhere in between these two values we are going to have the value, that is 4 edges discontinuous. This is 1.2, this is 1.3. Somewhere in between these two we are going to have the value, that is positive moment at mid span alpha x value. So this will be the alpha y value. You can see here now alpha y value, that is for the longer span. It will be 0.056 and 0.076, somewhere here in between these two. If you interpolate, you will get the answer. So therefore mux, so for that also they have given the formula alpha x into w lx square. Alpha x is 0.0, this is the formula, alpha x into w into lx square. So alpha x is 0.076, wu is nothing but 13.275, and lx square is nothing but the span, it is 4.1452. We'll get answer as 17.37 kilonewton meter. Then next is MUY, that will be equal to alpha y into W into Lx square. So 0.056 we have, 13.275 multiplied by 4.152. We'll get answer as 12.8 kilonewton meter. Then next is shear will be equal to WL by 2, that is 1 divided by 2 means it will be 0.5. We have WU is 13.275, LX is 4.145. So we'll get answer as 27.6 kilonewton. Then next is let us try to check the depth of the slab. So M will be equal to 0.138 FCK BD square. Why? Because it is Fe415. So therefore let us try to calculate this depth. So this will be equal to M divided by 0.138 FCK B. So square will be having square root here. So therefore D will be square root of 17. That is MU. Maximum moment what here, that is 17.37 into 10 raised to 6 divided by 0.138 we have, FCK is 20 and B is 1 meter. So you will be getting answer as 79.33 mm. So which is less than the provided depth, that is 145 mm. So therefore the effective depth selected is sufficient to resist the design ultimate moment. Then next let us try to calculate the minimum area of steel, that is 0.12 percentage of B into D. B is 1000, D is 170. So minimum area required will be 204 mm square. This is the minimum area of steel. Then next is let us try to calculate the reinforcement along short span and long span. We have this formula, or you can use another formula, that is AST is equal to 0.5 FCK divided by F of I into square into bracket of 1 minus square root of 1 minus 4.59 into mu divided by FCK BD. So by substituting in that formula, you take mu as 17.37, we will get area of steel as 302 mm square. So if you are going to adopt 10 mm dia bar, we have to calculate the spacing. So spacing will be equal to area of this 10 mm dia divided by AST required, that is 302 multiplied by 1000. So if you calculate, you will be getting spacing around 255 mm center to center. This will be in the shorter direction. Then next is, if you are going to use 10 mm dia bars along the long span, effective depth will be equal to 145 is the effective depth minus 10 mm dia. So therefore 135 mm will be the effective depth in the long span. Hence the reinforcement in the long span will be uh, calculated using again this relation. So here it is 12.8 we have. Therefore 12.8 into 10 raised to 6, that same formula I can use so as to calculate the area of steel as we had calculated here. So area required will be 237 mm square. So if you are going to use 10 mm dia bars, spacing will be, it is pi by 4 into 10 square divided by 237 multiplied by 1000. So you'll get the answer as nearly 300 mm center to center in the long span. Then next is, let us try to check for shear stresses. Considering the short span Lx and unit width of the slab, the shear stress is given by, always we have to take short span, and always we are considering the unit width, that is for 1 meter we are going to design. So tau is equal to Vu by B into D. So Vu already we have calculated, design shear, that is 27.6 into 10 raised to 3 kilonewton. We have converted it to newtons, divided by B into D, that is 1000 multiplied by D is 145. So therefore tau V will be equal to 0.18. Then next is, let us try to calculate the PT, that is AST by BD multiplied by 100. So AST provided is 302, B is 1000, D is 145 multiplied by 100. So you'll be getting answer as 0.2 Newton per mm square. Then next is, we have to refer the IS code and we have to find out the permissible shear stresses. So we will get K into tau C. So for M20 we have 1.26 multiplied by tau C will be 0.32. So if you multiply, you'll be getting answer as 0.4 Newton per mm square, which is greater than 0.18. So hence we can say that slab is safe in shear. Then next is, we have to check for deflection also. So L by D basic we have, that is 20, and the percentage of steel is 0.2. Again, if you refer what you can say the IS code, we can calculate the value of KT, that is in tension, or in the earlier videos we used to take F1, F2, F3, or K1, K2, KT, KC and KF we have. So for tension steel, we are going to get 1.7, that is 20 multiplied by 1.7, we'll get answer as 34. So L by D provided is 4.15 divided by depth provided is 145 mm. So it is 28.6. So therefore, which is less than 34. Hence we can say that it is satisfying the deflection criteria also. Then next is, we have to check for cracking. So as to check for cracking, we should see that the steel provided is more than the minimum percentage, that is 0.12. Then next is the spacing of the main steel, it should be less than 3 times the effective depth, that is 3 times 145, which is equal to 435 mm. Then next is diameter of the reinforcement, that should be less than depth divided by 8, 1/8 of the depth. So 175 by 8, so 21.8 we have provided what you can say 10 mm bar. So therefore this is also satisfied, this is also satisfied, and we have provided more than the minimum percentage of steel. Hence the cracks will be within the permissible limits as per the IS code. Then next is, they have said us to do calculation for torsional steel also. So area of the torsional steel will be equal to 75 percentage of what you can say the steel required, that is 302 we have. So here we have 302, we have to provide 37 3/4 of the area of steel. This will be 226.5 mm square. And up to what distance this torsional reinforcement should be provided, that is 1/5 of the short span, 1/5 of the short span. So here further I will tell you. So that is equal to, that is 1 by 5 is nothing but 0.2 multiplied by short span is 4000. So we will get answer as 800 mm. So we are going to provide the torsional steel up to like this distance of what you can say 800 mm. 800 mm. So let us try to provide 6 mm dia bars about 100 mm center to center for length of 800 mm at all four corners in four layers. Then next is reinforcement in the edge strip, that will be equal to minimum, that is 0.1 percentage of cross sectional area. It is 0.12 percentage, 0.012 multiplied by B into D, that is B is 1000, D is 170, will get answer as 204 mm square. And if you provide 10 mm bar, so spacing required will be around 300 mm square. So therefore we'll provide this in the edge strip. So if you see now, this is the slab we have, which is of size 4 meter by 5 meters. In this direction it is 4 meter, in this direction it is 5 meters. Then next what happens is that this is the short span and this is the long span. So along short span we have designed the reinforcement and we are going to provide the alternate bent up bars. This is bent up and this is straight. So here this is straight and this is bent up. So therefore we have provided the bent up bar and we have calculated the reinforcement along the shorter span, that is 10 mm bars about 255 mm center to center. Then next is regarding the long span. So this is bent up we have, this is straight, this is bent up. Here it is bent up, here it is straight. So along the long span we have calculated and the reinforcement got is 10 mm dia about 300 mm center to center, and in the edge strip also we have calculated, which is required is 10 mm dia about 300 mm center to center. So if you see this sketch in both the directions the bars are being bent up. So this is nothing but the two-way slab. In one-way slab only in one direction we are going to provide the bent up bar. So what should be this distance, that is 0.1 L is the distance. So as this is the short span, we are going to have 0.1 Lx. Then next is regarding the torsional reinforcement. So we are going to provide a mesh like reinforcement. So for this also we have done calculation, that is 6 mm diameter about 100 mm center to center. So what should be this distance? So what should be this distance? It is nothing but 1/5 of the shorter span. So shorter span is 4000. So 1 by 5, that is 0.2 multiplied by 4, it will be 0.8. So therefore up to 8 distance of 800 meter, 800 mm, we are going to provide the mesh. So here it is 800 mm, here it is 800 mm. So similarly you can provide on all the four sides. So in this what happens that this is the plan showing the details of the slab. So if you see the section, so you can see now this is the bent up bar we have and we have the straight bars. So if you see along the shorter span, if you cut you can see here the section has been cut. So this is section XX we have. So here if you cut the section, so what happens is that these longer, and if you are going to see it from here, so this bars will look like lines. So here what we are going to see like lines, they are nothing but this horizontal bar. These vertical bars, they are going to look like the dots, right? So therefore if you see this line is nothing but 10 mm dia about 200 mm 220 mm center to what you can say 255 mm center to center. Then next is what dot we are saying, that is nothing but this. So 10 mm dia about 300 mm center to center. Then next is at the top you can see now this is bent up bar, we have one straight bar. Next is regarding the torsional reinforcement. If you see this torsional reinforcement, up to what distance we have provided from this face of the column till 800 mm, that is 1/5 of the shorter span, that is 800 mm. So what is the reinforcement? 6 mm diameter, 100 mm center to center. So this reinforcement in both the direction, it will be 6 mm diameter, 100 mm center to center. Then next let us try to see another problem. So design a two-way slab for an office floor to suit the following data. Size of the office floor is 4 meters by 6 meter. edge condition, previously it was simply supported. So here we have two adjacent edges discontinuous. Two adjacent edges discontinuous. Material is M20 and grade is Fe415 HOST bar. So first let us try to fix the depth of the slab. So as the span is more than 3.5 meters, we can adopt span to depth ratio as 25, that is L by D ratio. So therefore depth will be equal to L divided by 25. So that is 4000 by 25, we will get answer as 160 mm. So let us adopt effective depth of 145 mm and overall depth of 170 mm. So next let us try to calculate the effective span, that is the effective span the short as well as long direction, that is clear span plus effective depth. So we have 4 meters plus effective depth is 0.4145, which is 4.145 meters. Then next is Ly will be equal to clear span plus effective depth, that is 6 plus 0.145, which will be nothing but 6.145 meters. Then next is let us try to calculate the load. Self weight of the slab will be equal to depth of the slab multiplied by density of RCC, that is 25, which will be 4.25 kilonewton per meter square. Live load is 4, floor finish is let us assume 1.5. Therefore total working load, if you are going to add up these three loads, it will be 9.75 kilonewton per meter square. So if you calculate the design ultimate load, we have to multiply it by 1.5. So 1.5 multiplied by 9.75, we will get answer as 14.625 kilonewtons. Then next is let us try to calculate the ultimate moments by using the IS code. First let us try to calculate Ly by Lx ratio, that is longer span to the shorter span. 6 divided by 4 is nothing but 1.5 we have. So for this let us try to calculate the short term moment coefficient and long term moment coefficient. So if you see the table we have, this is the table we have. So Ly by Lx ratio we have, which is nothing but 1.5. In these values we have to consider. Here two edges are discontinuous. If you refer the problem, two edges adjacent edges discontinuous we have. So here you can see two adjacent edges discontinuous. So this top value will be for negative reinforcement, and two adjacent edges discontinuous. This will be like top negative moment, and we have positive moment. Top value will be negative, bottom will be positive, that is 0.075 by 0.056. So if you see here 0.075, that is negative alpha x, what is positive alpha x, that is 0.056. The next is for alpha y value, you can see here 0.047 and 0.035, 0.047 and 0.035, that is alpha x and alpha y, that is negative moment coefficient and positive moment coefficient. Then next, based on this, let us try to calculate the moment. Same formula we are going to use what they have given. So alpha x we have, that is 0.075, w is nothing but 14.65, lx square, that is shorter span lx itself we take. So this and this will remain same, only this alpha x alpha y value they are going to change. So for negative it is 0.075, so you'll get answer as 18.85 kilonewton meter, and for positive moment it will be 0.056. Positive it will be 0.056, that is 14.07 kilonewton meter, and for long span moment it will be 0.047 here we have, and for positive moment it is 0.035. So you'll be getting answer as 11.81 and 8.8 kilonewton meters. Same formula we have, these things will remain same, only this alpha x alpha y value they are going to change. Then next, after calculating these moments based on this maximum moment, let us try to calculate the depth which is required. So therefore depth will be equal to 0.138 FCK BD square. So therefore D will be equal to mu, that is the maximum moment, that is 18.85 into 10 raised to 6 divided by 0.138 FCK BD square. So we will be getting answer as 82.64 mm, which is less than 145 mm. So the depth which is provided is sufficient to resist the ultimate moment, and AST minimum will be 0.12 percentage of B into D, that is 1000 multiplied by 170, which will be 204 mm square. Then next is let us try to calculate the reinforcement along the long span as well as along the short span. So same formula earlier to this what I had said, AST calculation formula, that formula you can use. Then next is if you want to do the calculation of spacing of a selected bar, we can calculate the spacing, that is equal to area of one bar divided by the total area required multiplied by 1000, and we have to provide the area of steel such a way that it has to be greater than the AST minimum required. So therefore, and in addition, the spacing should be at least 3 times the effective depth or 300 mm, so as to avoid cracking. And if you are going to use the 10 mm dia bars for long span, and for that D will be 145 mm, and for short span it will be 10 mm less. Why? Because we have considered the 10 mm dia bar, so it will, which will be 135 mm. So based on this, we can calculate the moment and we can calculate the spacing by using the 10 mm dia bars. So therefore, if you calculate AST is equal to 0.5 FCK divided by f of I into bracket of 1 minus square root of 1 minus 4.59 into mu divided by FCK BD square. So based on that formula, if you put the moment values what we had calculated earlier here, so based on these moments, we are going to get these areas. AST required will be 328, 242, 218 and 204 mm square. And if you are going to use 10 mm dia bars, and if you try to calculate, that is pi by 4 into 10 square divided by 328 multiplied by 1000, we will be getting approximately answer as 235 mm center to center, and for this it will be 300 mm. Similarly, here we are going to have nominal 300 mm center to center. Then next, if you are going to calculate the torsional steel at the corners, so area of the torsional steel will be equal to 75% of the area of steel required, that is 242 we have. This for a positive movement, so which will be 181.65. Up to what distance it has to be provided? So that is 1 by 5 of the span, that is 1 by 5 of 4 meters will be 800 mm. So 800 mm in both the directions we are going to provide the torsional steel. So if you we are going to provide 4 layers of reinforcement at A with 4 bars of 8 mm dia. 4 bars of, if you see, this is the what you can say slab, we have 2 adjacent edges, this is continuous and this is continuous. So you can see here now they have shown the continuation mark, that means these two sides are discontinuous, continuous, and these two sides are discontinuous. So therefore here reinforcement required will be full torsional reinforcement. So here one edge is continuous, one edge is discontinuous. So therefore here required will be 50%, and here it is continuous. So therefore no need to provide the torsional steel. So therefore at B we have to provide the 50% of the torsional steel. That is, we can provide 2 bars of 8 mm dia in each of the 4 layers. At point C, torsional steel is not required. So this is the sketch which is showing the slab. This is our slab of span 4 meters by 5 meters. This is one another slab, and this is another slab. So therefore this is, they have shown the continuation mark. So therefore we have 2 adjacent edges continuous and 2 adjacent edges as discontinuous. So if you see now, this is the reinforcement which is being provided. You can see now 10 mm dia bars, what you can say, along short span, it is 235 mm center to center and 300 mm center to center. So positive bending moment, we have to provide 300 mm center to center. So this is now at the center, maximum, what you can say, along short span, that is 10 mm diameter, 300 mm center to center. The next is the negative reinforcement, it is 235 mm center to center. 235 mm center to center. Then next is along long span. Now this is the long span we have. So we are going to provide 10 mm diameter, 300 mm center to center. 10 mm diameter, 300 mm center to center. So this is the reinforcement what we have, which is 10 mm diameter, 300 mm center to center. And along long span we have to have 10 mm diameter, 300 mm center to center, and the slab thickness is 170 mm. So in this way the detailing of steel has to be done in the slab.